This particular chapter is 100% vocab related, conceptual related. I had written down on the test that the first year the kids took this test, they got an average of 87, which is a really high class average. But then I have written on here the third year the class took this test, it was a 73. So that's like a 15% difference from one year to the next.
Did you say 86?
What was last year?
86 is an extremely high class average. A B plus is not average. A C is average. So 73 is probably where it should be. But
above average.
Not everybody. Yeah, 87 is a really high class average. Okay, so just kind of giving you guys a little heads up on that. So what we're going to talk about today are trends that we see on the periodic table. The very first trend is radius. We should be familiar with what radius is, right? Maybe not what the atomic radius is, but we should know what the word radius is. Yes?
Yes.
What is the term radius?
The distance from the center to the outside of the circle.
Okay? So if we were to draw a circle, there would be your center, there would be the outside, and that would be your radius, correct? Okay, if I'm talking about atomic radius, what do you think it's referring to?
The distance from the nucleus to the outside of the electron.
Yep. So in the middle of the atom is the nucleus, and on the very, very outside of the atom, or the place that you would say would be the furthest out the atom could be, would be its outermost valence electrons. Okay? So we are going to see some trends as we progress across and up and down the periodic table for radius or size. Okay? Now, there is a why behind all this stuff. Can you get by with just regurgitately memorizing the trends? Yes, you probably can on some questions. Okay? But it's far more beneficial to know the why. Alright? So it says that the atomic radius is the distance from the center of the atom's nucleus to its outermost electron or its valence electrons. And it says the radius decreases going left to right. So left to right, it says it decreases. And then it says it increases going from top to bottom. Will everybody remember that L and R is left to right and T and B is top to bottom?
Yeah.
Okay. Right, now let's explain this. Okay? If atomic radius is the distance between our outermost electrons in our nucleus, you can see how that might change based on the amount of electrons we have, correct? Or what energy level these electrons are in. Because we said as the energy level goes up, the distance the electron is away from the nucleus goes up or down.
Further up.
No, I'm saying as the energy levels increase. And that has nothing to do with what I just put on the board. What you know about energy levels. As the energy levels increase, are the electrons spending time further away from the nucleus or closer to the nucleus as you get higher in energy levels? Further away, right? We talked about kind of first energy level, second. I know it's not like Bohr's model and that they're orbiting like planets orbit the sun, but in general, as the energy levels increase, your orbitals are getting further away from the nucleus. Okay? Very important. So I would say the top to bottom is the easiest to explain. Let's look at it this way. So as I go from top, whether anywhere on the periodic table, if I start on the top and go straight down, okay, the radius of these guys is going to what? And this should make sense. Here's why. Let's say we're talking about lithium in the second energy level. Only got 3 electrons, correct? Okay? As I go down to sodium, I have many more electrons, and I added another energy level. Should be further away from the nucleus, right? Giving it a bigger what?
Radius.
radius. So let's just say we're using the Bohr model. I know the Bohr model is not completely accurate, but do you see how as I progressively go down the vertical columns, I'm increasing in energy levels. So let's say there's my first energy level, there's my electron in my second, there's my electron in my third, there's my electron in my fourth. Do you see how the radius is getting bigger?
But I thought that like the gases would have more energy because that's how it is in phases. The solids have less energy and those are solids. Does that have
It has to do with their intermolecular forces and the things that hold them together, not just energy alone. It's never usually one thing dependent on anything in chemistry. There's always a second or a third thing that also plays a part. Okay? So, top to bottom, adding energy levels, getting further away from the nucleus, the radius increases. That makes sense. Yes? Okay. Sure. All right? The left to right is a little bit more tricky to, I shouldn't have erased that. A little bit more tricky to understand because it says as I go from left to right, the radius what? Decreases. Okay? So listen very carefully. I'm going to try to explain this as best I can, but I don't want to have to re-explain it a bunch of times because you're not paying attention. Okay? So let's just think as if we're dealing with the second energy level. Okay, it becomes more difficult if you like change the vertical column and the horizontal column at the same time. So we're just going to focus on one particular energy level in this case. So let's say I am going in the second energy level left to right. Okay, as I go from left to right, don't I increase in the number of electrons? Wouldn't that make the orbital or the radius bigger? Wouldn't you think adding more electrons would increase the radius of a particular element?
But it has to be filled for.
Okay, that's true.
Okay. Yep. The number.
Well, they all have the same amount of energy levels.
Okay, so they're all in the same energy level. Now, we do know that as you progress, you get to different orbitals and sublevels, correct? Okay? But here's the thing. A lot of times we think, oh, just because we're adding electrons, therefore it has to be getting bigger. But aren't we also adding the same number of protons as well? Okay? But we're staying in the same energy level. Okay? The reason why this gets bigger is because we're adding more protons as well, but we're going down in the amount of energy levels further away from the nucleus. Here we're staying in roughly about the same energy. Okay, so here's what happens. Listen very carefully. Okay? Each additional electron that gets added is not as effective in shielding other electrons and repelling it to make it bigger as each additional proton is in pulling everything closer to the nucleus. Okay, does that make sense? Because you know, as we're adding, so say this is the nucleus, right? And we'll go back to the Bohr model, right? So our first energy level can only have 2, correct? Okay, then our second energy level we can add up to 8. Okay? Well, as I'm adding electrons, yes, these electrons are negatively charged, and they really kind of repel each other, so it would kind of shield itself and really make it bigger. But we're also adding protons in the middle here. So as you add protons, for whatever reason, the protons are really twice as effective in pulling all of the electrons closer to the nucleus as an additional electron is in repelling everything else away from the nucleus. Okay? It's kind of tricky. Did you hear me, Brevin? You sure? Okay? So what happens is each additional proton is more effective at pulling the electrons closer to itself, making the radius smaller, right? Than the additional electron is in repelling other electrons away from the nucleus. Okay, or making it bigger. So as we go from left to right, assuming we stay in the same what? Energy level. Okay? If we stay in the same energy level, we're at relatively the same amount of energy. As I go left to right, the protons are better at pulling towards than the electrons are in shielding each other and making it get bigger. Right? Next one. So there's an example. Now, the group 7, or the F block is really goofy in that these are actually smaller than that one. There's really no good trend for the F block, but those are the radioactive man-made guys, and so that's a whole nother issue. Don't worry about the F block, okay? As a general rule though, as I go down I get bigger, even if I'm over here. As I go down I get bigger. Okay? And as I go from left to right I should get smaller. Bigger here, smaller, 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 and so forth. Okay? All right, ionic radius. This should be probably the easiest to explain. However, this has nothing to do with location on the periodic table. This is just comparing a neutral atom to its ion form. Does that make sense? Okay? So let me explain what I mean. It says cations are smaller than their neutral atoms. Okay, let's try to identify what a cation is then.
Positive.
Okay, so let's say I had calcium atom and then I gave that calcium a 2+ charge. What's the difference here?
Well, the 2+ has 2 less electrons.
Okay, so this, they both have the same number of protons, correct? But this one has 2 less electrons. Well, wouldn't the protons in the nucleus be able to pull on the remaining electrons more than if you had the full amount of electrons? What would that do to the size? Make it smaller. Okay? Anions are larger than the respective neutral atoms. So let's say I'm talking about chlorine, and I have a -1 charge. Okay, versus a regular chlorine atom. They both have the same number of what? Protons. But chlorine has an additional electron, so therefore it's going to be slightly bigger. Pretty easy. This one's much easier than the more difficult left to right atomic radius concept. Okay? All right, last one for today. Questions so far? Are we doing all right? Yeah? Okay, ionization. All right, left to right, top to bottom. So before I get into explaining this, let's just identify what the trend is. Ionization energy increases left to right. And does what? Top to bottom. Say right there. Decreases. Now how does ionization energy relate to atomic radius? They are opposites. So guys, you only need to memorize one of the two if you want to do it the memorization way. Which is, again, not the best way, but it is a way. Because if you know one, you should know the other if you just know they're what? Opposites. Okay, and here's why they're opposites. Ionization energy is almost solely dependent upon the radius. Now let me explain. Okay? So here's the definition of your first ionization energy. Now there is a second, third, fourth, and so forth, but you won't study that unless you take advanced chemistry. Because we're just going to talk about the first guy. It says the minimum amount of energy required to remove an electron from its outermost energy level. Okay? So it's essentially how much energy is required to remove a valence electron, the first one. Does that make sense? Okay? Now that is going to be very dependent upon radius. Some atoms hold their electrons much tighter than other atoms. And a lot of that has to do with radius. Let me show you what I mean. All of these guys have how many valence electrons? 1. Okay, so if I wanted to remove that one valence electron, which one would be the easiest to remove? And could you tell me why you would think that? I'm hearing whispers, but no one's confident to try to explain why. What? Want me to re-answer the question? I said, which one of these guys, they all have one valence electron, right? Which one would be the easiest to remove that valence electron from? Francium. Why? Because what? Because it's farthest away from the nucleus. Remember, it is the protons in the nucleus that are holding the electrons together, right, Tanner? Isn't that correct? It's the protons in the nucleus that are holding the electrons together. Well, since francium has so much more energy levels, its electrons are much further away from the nucleus, they already have high energy, they're fairly easy to remove. So this would take the least amount of energy to remove an electron. This would take the most amount of energy to remove an electron because this electron is very, very close to the what? Nucleus. Does that make sense? Okay? So I would say it would take the minimum amount of energy, the least amount of energy to remove francium's electron than it would be to remove hydrogen's electron. All right? Well, if we go left to right then, does that agree, first of all, top to bottom? Okay? The amount of energy needed to remove an electron is going to decrease as you go top to bottom. Or it's going to increase as I go from bottom to top. More energy required to take the electron away from hydrogen because it's closer to the nucleus. Much less energy needed to take the electron away from francium because it's further away from the nucleus. We follow that same concept. As I go from left to right, is this or this got a tighter radius?
Argon.
Argon has a much tighter radius, so which one would be harder to remove an electron from? Argon. Now harder would mean take more energy, right? Okay? As you go from left to right, it takes more energy, or it increases in the amount of energy needed to remove a valence electron. Everyone see it? Tanner? Sit up. I think that's it. Questions? Yes.
So, does that mean that fluorine
Chlorine.
would take really easily, take very strongly?
What do you mean take very strongly? Like, yes. So we'll talk about that tomorrow. How fluorine would have a strong electron affinity because one, it only needs one to complete its full octet, and two, its electrons are a lot closer to the nucleus, so it has a stronger pull on electrons than, say, lithium or sodium. So that's, yes, we're going to get into why in the world do the metals tend to give and the non-metals tend to take. What has to do with their desire to pull electrons towards themselves. And we're kind of talking opposite, desire to not need the electron. Right? Francium doesn't really take much energy to take an electron away from francium, so it willingly gives it. But fluorine, you're not going to take an electron away from fluorine very easily. It's going to take a lot of energy. Yep, you're getting into where we're going to be getting into probably tomorrow. Wednesday we will not have class, as you guys would probably assume.